has heard of Lawrence Livermore National Laboratory? Okay, so a fair number of people. I have some high-level slides for everyone else. Just to get started, Livermore is a Department of Energy national laboratory. We do a lot of work on behalf of national security missions. For those people who don't know where it is, Livermore is about an hour from here. It's over the hills past Oakland, past Pleasanton. And the lab itself is about 6,000 people in 1 square mile. And we do a lot of science. So who's seen Star Trek Into Darkness? Anyone? Anyone see that? No? Okay. Well, this is the engine room of the Starship Enterprise, but that was actually filmed at Lawrence Livermore. That's a giant laser that we have for doing high energy fusion experiments. And that's the sort of target chamber there. It's the center of about 192 lasers in a building the size of, say, 3 football fields. And they fire at something that's about like this big to implode it, and we can learn about stars, supernovae, and nuclear explosions that way. And to do that, we require a lot of computing power. We try to simulate all the physical things that we study at the laboratory. All the different programs at Livermore rely heavily on computation. And so, if you imagine, something kind of like the machine learning workloads that you would see in the cloud, but for really big science problems, instead of, deep neural nets, that's kind of what we have at Livermore. And this dates back to the origins of the laboratory. We've relied on computation like this since 1952, although maybe in 1952 the machines weren't quite this big. We have some of the top-ranked supercomputers in the world. Sequoia, you may have heard of. It's got 1.5 million cores. That's the machine that's pictured right there. And you can find stuff about these machines on like the top 500 list and places like that. We are known for some of these fast machines, but Livermore actually has a whole lot of machines that we care about. We have a compute center of our own. It's 48,000 square feet. We've got something over 2 million cores in there across 42 Linux clusters and some Blue Gene machines as well. And for the software, so this is a multi-architecture environment. We care about getting the most out of our hardware. And that's what the server floor looks like in that building. We also have some other compute centers around campus. So why do you care about this, and why do we care about this? The software that we run on these machines is really complex compared to maybe the more luxurious cloud ecosystems that you're used to. Building HPC software can be pretty complicated because we care about performance. And because we have security concerns. We have the center, it's devoted to something like 3,000 to 6,000 users use the machine. Most of them are building software in their home directory. It's not quite like getting your own image and installing software with the system package manager. Users typically build from source themselves to optimize for the hardware. And there's not a lot of standardization. The different machines are unique. Different DOE labs, not just Livermore, but Argonne, Oak Ridge, Los Alamos. All of these places have sort of similar environments, and people are building to get the most out of the hardware. And this gives us this combinatorial software complexity problem that we find pretty hard to manage. So here's an example. This is a Livermore code. We had something like 48 third-party packages. Keep in mind these are native libraries. It's not all JavaScript. We care about something like 3 MPI versions. That's the message passing library that we use for communication among jobs in these massively parallel applications. 3 platforms maybe. We care about Cray because other sites have Cray machines. We run on those as well as our Linux and Blue Gene clusters, and we may care about ARM in the future. We're always looking to get more out of hardware. Up to 7 compilers, and maybe 2 or 3 versions of each package because of minor incompatibilities between all of these things. So that's like 7,500 combinations. That's not a fun ecosystem to maintain. And so we needed a tool to reduce this complexity by automating these types of builds. And just to kind of give you an example, here's one of our multi-physics codes. This is a radiation hydrodynamics code. It models things like those NIF targets that I was talking about. This has 47 dependencies in C, C++, Fortran, Python, Tcl. And this code dates back to like 1996. So that's a lot of validation and effort that went into this. And we care about porting it all the time to new platforms. Users of HPC centers are not quite like your cloud users. They tend to be scientists and computational scientists, and they build things themselves. They're supported by user support teams at HPC centers who kind of help them by installing facility software and also by answering technical questions. And then, HPC application teams also build and distribute these apps for the different platforms. So, there's a lot, I would say, more collaboration. It's not like the developers all just get an image and build on that. There's much more of an interlocked ecosystem here than maybe what you're used to from a cloud center. So to deal with all of this and to try to bring the ecosystem together with a unified software stack, or some glue at least, to help manage all the software, we built Spack. And Spack it's a flexible package manager for HPC, and what I mean by that is that we want to make it easy to install HPC software, but we also want to make it easy to customize. And I'll get into that a little bit later. But in the most basic case, we want it so that these users who are not sophisticated system administrators can just clone Spack off of GitHub. They can go there, they can say git clone Spack, add it to their path, and then say Spack install, say HDF5, which is a IO library. And its dependencies are installed like you would expect. We also want to be able to build that thing with different compilers, different dependency versions, different build options, different compiler flags, and so on. And we care about things like cross-compilation. And so I'm going to talk about how we do that. So you can see what's available in Spack like you would expect with Spack list. This is, you could say, Spack list at the terminal. We have over 1,800 packages. And these are all just the names of the packages. We also provide a spec syntax. We call it the spec syntax, to describe how we want to install these things on a machine. So again, in the most basic case, you say Spack install foo, and you get foo. You might want a specific version of it, so you could say at version. You can say, I want to build it at this version with this compiler at a particular version. You could say add a build option on the command line. You can inject flags into the build. And you can also do things like on the Cray, you can build for a particular architecture. So some of these machines have multiple back-end architectures on things like Haswell and Xeon Phi. So we have a syntax for that. And then finally, that syntax is recursive, so you can basically say caret mpitch if you depend on mpitch and specify a version of your dependency. And the idea here is that you can specify constraints on your DAG. You can basically say, I want to build exactly this thing, but you don't have to know the structure of what you're building. You don't have to know all the dependencies for this thing or provide a full spec. You just say what you care about, and Spack fills in the blanks for you, or that's the idea. How do we do this? Spack is designed to handle this combinatorial complexity for you. And so if you imagine that this is your project, that's a dependency DAG. Every unique configuration of that DAG, where each node in that is a package, and those are the dependency relationships, every one of those configurations gets a unique hash. And this is similar to systems like Nix. It's a little different in that it's not a binary hash for binary reproducibility, it's a hash of the metadata. So it's basically the DAG configuration with compiler and metadata, all the things that I showed you on the previous slide. And the way that we make them coexist is that we embed our paths in the binaries so that essentially every library knows where to find its dependencies on disk. So we can have all these DAGs coexisting in the same Spack install, and they know where to find each other. We've developed this process called concretization, which is essentially fancy dependency resolution, where you take that syntax from the command line, you get a loosely constrained DAG like this. We convert it into a concrete DAG, which gives you basically Spack fills in all the blanks and gives you a complete spec, something that you can build so you don't have to ask any more questions. And we'll store the provenance for that on disk. And once you've done that, you can use the same syntax to query what's installed. So you could say Spack find, and this shows you all the different builds that you have installed. Notice that some of them are the same version coexisting with different properties that you can't see in this view for different architectures and different compilers and different platforms. We generate module files for this, which is kind of how people use, or how they set up their environment on HPC systems, and we're working on building environments more like Nix or Conda that people are maybe more used to in the cloud space. You can also go and query that provenance, so you can say find call path. This is a library that we use to sort of introspect stack traces at runtime. And you can see that there's two versions of the thing there. You can go and look at the whole dependency configuration and use that to debug things like, oh, that doesn't work because that one uses that version of Boost and this one uses this other version of Boost. Spack also, so this is maybe one of the unique things about it, is that it manages installed compilers. You can build things with different compilers, and we actually care about that, whereas there aren't many package managers where I see that being a first-class citizen. You can set it up, it'll automatically detect the compilers on your system, but you can set it up with more compilers. And we build each package in its own compilation environment. So when we fork the build, we actually use compiler wrappers, and this is how we inject the RPaths automatically while still making it easy for people to write packages for Spack. We inject custom compiler flags into the builds, and we're working on things like adding tools here so that you could do things like maybe LLVM instrument a binary with Spack from within one of these compiler wrappers. That's not in there yet, but I'd like to do that. I think it would be pretty cool. We have tried to make contributing to this pretty easy. We wanted to make the package format intuitive for people in the HPC community. So this may look familiar to people who've written a homebrew package ever, but it's in Python. And the reason for that is that there aren't that many people in HPC who know Ruby, but there are a whole lot of scientists who know Python. And so this is a much easier language for people to adopt. There's one package. It's essentially a templated build for all the different versions, architectures, ways that you would build that package, which means that you can take that package and you can do things like the syntax I described. You can try new configurations that maybe someone hasn't set in stone yet. You can say, I want to build that with a different version of the dependency. And in the build, we can use the syntax that we developed to say things like, if I'm using that other version of this dependency, then do something special, address some issue with it, or patch it. We have gotten more contributions than we thought we would to this project. We started, I guess, in 2013, and it kind of trudged along for a while until maybe 2015. You can see here, it was mostly a Livermore project up until 2015. But since then, since we gave a presentation on this at Supercomputing, the number of contributors has really skyrocketed, and it's gotten to be quite a busy project. We've got support from the other national labs and also industry. So like we have some people from Genentech and also from other institutions like EPFL in Switzerland. And so we're pretty psyched about that, but it's organized chaos like any open source project, and we're working on integrating all the pull requests. We have heard from ARM that they are using Spack to test their compilers. I don't know how extensive that is, but I think that's pretty cool. And we also have users at a lot of different scientific institutions. So NASA is using it for ice models. The LIGO collaboration, these are the gravity waves guys, are using it, and a whole bunch of others to package software for HPC. And on the roadmap, like I said, we're looking at adding better environment support so that people who are used to a laptop can use Spack more easily. We're looking at binary caching so that you could cache optimized binaries on a server, say out in S3, and pull down maybe an ARM v8 optimized or Haswell optimized version of a package instead of having to build it. And then we're working on improved dependency resolution to support all that. So join us on GitHub. Like I said, contributing is simple. There's the URL. Go there, start our project, and we're on Twitter and Slack, so hope to see you all there, and hope this is useful to you. Any questions?
We meet in the center, in the middle. Actually, a question regarding your package manager. Does it really integrate with the distribution package manager? Because the usual problem with such things is that, well, it's great as all the Perl, Python, etc. package managers, but then you have files that are not managed under the system, and that's bad.
Yeah, so how to answer this? So that's a major feature of Spack because we do care about integrating with the system, especially because we're in HPC, right? If we don't use the system MPI, then we're dead and we don't get good performance. So you can, for any package in the DAG, specify an external. There's a configuration file for that right now. So you can add the system BLAS, the system LawPack, the system MPI, things like that. Like I said, we detect the system compilers and build with them. And one thing we would like to do in the future that's not there right now is detect system packages. And so we might know what's on CentOS, for example, and just generate you a sensible default external file. But right now you have to specify that by hand if you want to use it. Otherwise, it'll build it for you.
I was asking about quite different thing.
Oh, sorry.
So, yeah, that's good that you answered still. Can I really, after I install some software with Spack, for example, on CentOS node inside my cluster, just then use RPM or YUM to delete that software?
Oh, so take RPM and install the thing that you built with Spack?
Yeah, so can I be sure that Spack software doesn't override system files, and if I update the system, that new system files will not override Spack files, etc.? So that would be my question.
I mean, so we have done Spack RPM generation at Livermore, although it's not in the mainline yet. And these things build entirely in user space, so they shouldn't interfere with the system versions of things.
Okay.
We do rely on system glibc right now.
Yeah, of course.
And so, there's a certain level at which we rely on the system, but these are isolated. So you can have, 2 versions or 16 versions of anything, and the R paths should make them find their own dependencies.
And everything gets installed into the user path or to the system path?
We don't add them to paths for you right now, but you can add, so the modules provide that functionality.
Yeah, okay.
Yeah.
Perfect, thank you. Yeah.
Yep.
So multiple users in the same clusters could install different Spack packages and see the cluster in a different way because they can just set their own paths to different things. So nothing in the system is overwritten.
Oh,
Yeah. Thanks.
Cheers.
I'm having trouble hearing.
Yeah. Another question I had for you is, when you have the dependency, it's not really a specific version dependency. It could be a range of version dependencies.
That's true.
And how do you control this when you say, well, this depends on this, which one do I build or do I pick? And if I specify a specific version and say, okay, this is able, but if I just look at that tree between like GCC and LLVM that you've shown,
Sure.
and so there's the different boost version, but this is just because one of them goes further, it doesn't mean that they're not at the same. You see what I mean? It's hard for the user to see.
Yeah,
So if you show the range, then the user can say, well, okay, both boost versions are okay for me on either compiler, so I'll just pick either one.
Okay, so dependency resolution is something that we're working on. Currently, I mean, the resolver will just, it'll pick the latest version of something.
Yeah.
Unless you specify you can specify a preferred version in the package, so we can manage the distribution somewhat that way. I'd like to get more control over that, and so that's something that we're working on right now.
Okay.
Yeah.
But it is an open source project, right? So
It is, yeah, so people can definitely contribute. Dependency resolution's a major focal point right now. And then, you can always specify the version on the command line. So if you want to override what it does, and we have a preferences file where you can say, always use this version of this other thing. And so there's a packages.yaml file where you can say, I prefer, GCC 447 and then 483 if that doesn't work, things like that. Yeah, so we do have some degree of preferences in there, and it's fairly extensive. Yeah.
So besides building these binary packages,
Yeah.
will Spack allow you to launch these onto a particular hardware, server, or desktop?
We're not providing launch capability right now. Essentially, so for the HPC systems, what you typically do is build in your home directory on a shared file system, and then run on the cluster, and it has that file system mounted. And so that's typically how people would use Slurm or something to launch the software.
Right.
Is that what you mean?
Somewhat, but you started saying that in your environment you had permutation of 48 type of things,
Yes.
and so about 7,000 things.
Sure.
So for those scientists that have actually access to 7,000 things,
Yes.
would they not want to say, build this thing for me for the best suitable hardware?
For the best hardware.
Yeah, instead of specifying, yes, I want a Haswell, I want this particular GCC, this particular, why wouldn't it say, build it the best it can run?
Okay, so 2 things. One, we don't actually build 7,500 versions of things, and it's a system for sampling that space. So there's that. The second thing is, so I agree that it would be awesome if we could build everything for the best hardware. But oftentimes we don't know that. And so, the point of this system is to allow people to experiment so they can figure out, how does this thing perform in different configurations on these machines? So yeah, I'd like to get there.
That's a challenge then for,
Yeah,
for the
that
community.
is definitely a challenge.
Build it.
Well, but then again, if you use O2 or O3 or this flag and that flag, and you get 20% performance, so you want to keep this into a spec file, right? To say, well, once I found the best one,
Yeah.
always use this. But the user has to then fiddle.
You do have to fiddle for that.
Yeah.
So, I mean, exactly.
But you have to
And
write the genetic
so-
algorithm to, yeah.
So we do have computers to fiddle, but there's not a lot of optimization, or there's not a lot of automation for this kind of build with different compilers. And that's what this is providing. And so, I think it would be an awesome thing for someone to come along with an auto-tuner and hook it up to Spack and build a zillion versions of things and tell me which ones are the best.
That auto-tuner would also be... No, hold on, I was going to say that
There are people
auto-tuner would also need to take into account the application space, because the parameters that work for one application space doesn't necessarily work
True.
for another.
Yeah. Well, and also, I mean, so another thing that it can even be data dependent. So we have applications like AMR applications where the kernel can
Yeah.
take different input sizes. And depending on those, you may want to use different flags or different, you might want to use a GPU, you might want to use a CPU. And so there's auto-tuning, there's jitting and other stuff that could be done on, you know, on top of this, but we're just trying to automate the build here.
But yeah, no, what you say is an optimization problem, and that is something to be considered, but there's lots of parameters to be considered. No. We're in agreement that there's a problem space here and it needs to be solved.
Yes, we would love for people to explore this problem space.
Yeah, just one thing for you is that this is coming up already in the acceleration piece. So we had the accelerator birds of a feather yesterday. And it's how do I actually query the system to know capabilities, right? And today we have a bit of that, but not a lot. And there's not microarchitecture detection. There's not a way for me to go and say, oh, look, I've got these ASICs on here, FPGAs, and I've got this capability. So that work has to start. But it's not just for HPC. I mean, it's for all the AI applications that are, all of that. So I think we're aware, us in general, all of us, right? But we also know we don't have anything.
We're still going to create small houses.
Yeah,
Yeah.
right. Yeah. Any other questions? All right, well, again, visit us on GitHub and hope to see you out on the interwebs. Thanks.